This video is about solving rational equations. And to do this, our notes will say this. We're first going to clear the fractions. It's not any different with rational equations than it was with linear equations that just had fractions involved with them. So we'll review that as we do it. And then something that is new for rational equations is that we have to check for extraneous solutions by just plugging our answer in at the end to make sure everything works okay. Now there's one key warning that we also want to observe with rational expressions, and that is we only clear fractions, which was, remember, our first main goal in this process. We only clear fractions if working with an equation. So it's all tied together, but it's really easy to kind of gloss over and get lost with all these words, especially when they all start with E. So, for example, we've also been working with expressions, but the difference is that with an equation, you actually have the equal sign showing up somewhere in the problem, whereas with an expression, you do not. You might have minus signs, plus signs, all kinds of symbols, but no equal sign. So when we see an equal sign, that's our clue that we're allowed to clear the fractions. Let's look at an example where we want to solve the following equation. It reads x plus 5 over x minus 2 equals 5 over x plus 2 plus 28 over x squared minus 4. Well, our first step is to clear the fractions, and to review that process, we first must find an LCD. But in this case, notice the denominators of these fractions are polynomials, and in that case, we may have to factor some of these in order to find the LCD. And as you can see, one of the denominators, the last one, which reads x squared minus 4, is factorable. So we should start by factoring that. I'm just going to write the factored form of it right underneath. So x squared minus 4 would factor into x plus 2 times x minus 2. That's just a difference of two squares. And in that case, now that everything's factored, we can put together our LCD, just like we would if we were adding or subtracting rational expressions. It's no different. Given all these denominators, x minus 2, x plus 2, and then x plus 2 times x minus 2, our LCD would be x plus 2 times x minus 2. And the order of those doesn't matter. You could put the plus or the minus first. Now, here's the deal. When you have an equal sign, and again, that's the main key here, that's your clue on what to do next. If an equation, like we see here, we can clear the fractions using the LCD, and we clear the fractions by multiplying the LCD across all numerators of all the terms on both sides. So it looks a little messy at first, but then it gets nice quickly. What we're going to do is start by recopying our problem, but we're going to put all of the original terms, so x plus 5 over x minus 2 is what we had on the left side. I'm going to put that in parentheses, and then we're just going to space things out to leave enough room to be working with all this, and then keep copying all the original fractional or rational terms down. So 5 over x plus 2 was our next, plus, and then lastly we had 28 over, and then I'm going to use the factored form of that last denominator. It'll just make it easier for us in the next step. So I'm going to put x plus 2 times x minus 2 as that last denominator in factored form. Then, to recall, the process of clearing the fractions involves us taking our LCD and multiplying all the terms across the numerator by it. So next to each of my original terms, I'm going to multiply by x plus 2 times x minus 2. Now the whole point of doing this is that if we've actually found the correct LCD, all the fractions should reduce. Now look at all the way to the left. There's an x minus 2 in the denominator, but also 1 in the numerator, which would cancel with it. Moving across the equal sign now, on the right side, there's an x plus 2 in the denominator that would cancel with the x plus 2 from the LCD. And then lastly, all the way to the right, both terms of the denominator, x plus 2 and x minus 2, will cancel with both terms of the LCD. We'll then rewrite whatever's left of this problem, which would include x plus 5 times x plus 2 on the left side of the equation. On the right side, notice we still have this 5 in the numerator, so we're going to keep that, but then distribute it to the terms in the binomial that's after it still. So in other words, we'll have ultimately here 5 times x minus 2 in parentheses. I'll distribute that at the next step. And then continuing on, we'll have plus. Similarly here at the end, it's just a 28. Both of those other factors of the LCD were canceled. Now we'll solve this as a quadratic equation by foiling the left side, which currently stands as x plus 2 times x plus 5. If we FOIL that out, we'll end up with x squared plus 7x plus 10. On the right side, we'll distribute the 5 to get 5x minus 10. And then we have our plus 28. And now this is just a quadratic equation we can solve by combining like terms. So let's go ahead and continue to finish that off. We have x squared plus 7x plus 10 on the left side. On the right side, we can combine the negative 10 and the plus 28 to end up with 5x plus 18. And then we want all the terms on the same side, and we'd like them where the squared term is already positive. So I'm going to bring the terms to the left side, which would involve subtracting the 5x and the 18 from both sides. That will result in x squared plus 2x minus 8. But then that's all equal to 0. To solve this remaining quadratic equation, we can use any of our quadratic methods. We'll try factoring, which is often the quickest if it's possible. It does seem like this trinomial we have left is factorable. We should try maybe an x plus 4 and an x minus 2 using maybe a guess and check method for factoring, or there are various other methods to factor a trinomial. Now that we have a product equal to 0 after factoring, we can use the zero product property, which would have us set each of our factors to 0 and solve. So x plus 4 could be 0, or x minus 2 could be 0, which means our results would be, if I subtract 4 from both sides, x equals negative 4, or x equals positive 2. Now, as you'll recall from our notes above, one very important step with any rational equation is to check our answers. So we'll do that simply by plugging them back in the original equation. To check negative 4, which is a proposed solution, we want to plug it back in for x in the original equation, which would tell us negative 4 plus 5 instead of x plus 5 over negative 4 minus 2 equals, or we're wondering if it's equal to, I'll put a question mark above the equal sign. We're wondering, is that equal to 5 over, and then negative 4 plus 2 plus, and then 28 over negative 4 squared is 16 minus 4. Now, this is just an arithmetic problem that could be done with the assistance of a calculator or done by hand. Either way, this one will turn out to work out just fine. In other words, the left side does equal the right side, which is good news. We'll continue by checking our other proposed solution. So we also must check 2 by plugging it in the same way. So is 2 plus 5 over 2 minus 2 equal to 5 over 2 plus 2 plus 28 over 2 minus 4. Now, it's the same kind of arithmetic simplification, but you can draw, I think, pretty quickly to one potential issue. Notice that all the way on the left side, the denominator ended up as 2 minus 2, but that would, of course, be 0, and we're not allowed to divide by 0, which means we have a problem. That means we have to call this proposed solution of 2 extraneous. In other words, we found it as a solution in our solving process, but when plugged in at the end with our check, it doesn't actually work. So we label negative 4 as the actual solution, and then 2 as an extraneous solution. Now, as a little note here, many textbooks, when giving the answers to a problem like this, would include the answer that we got as negative 4, but then they would just not list the extraneous solution. However, I prefer, for work done in class for it to be listed like you're seeing it here. In other words, I labeled 2 as a solution, but it's extraneous, and so I wrote that word right with it. Let's try a second example of solving a rational equation. This one reads x over 2x plus 7 minus x plus 1 over x plus 3 equals 1. And in the same way, we'll follow our basic steps, which involve clearing the fractions. But to do that, we need to find an LCD. And of course, to do that, we need to make sure all the denominators are factored. Well, if you look at these two denominators of 2x plus 7 and x plus 3, they are both already factored, or you could say not further factorable. So we'll leave them as they are, and in fact, just use the product of them as our LCD. So 2x plus 7 times x plus 3. Which means to clear the fractions, we're going to multiply all the way across by those. I'll copy the original terms down as they are, but in parentheses, and just leave some extra space to be able to work on this. And then we'll be multiplying by our LCD across the numerators only. So with the first fraction in the numerator, I'll be multiplying by 2x plus 7 times x plus 3. Same thing for the next numerator. And then in this problem, notice on the right side of the equation, there was simply a constant, the number 1. It's easy to forget that that also needs to get multiplied by the LCD. It's not a fraction, which can make it easy to kind of gloss right over and forget to do this, but every term on both sides needs to be multiplied by the LCD. When we do this, of course, things cancel all the way to the left. The 2x plus 7's cancel. Secondly, going on to the right, the x plus 3's factors cancel. Then we'll rewrite what's left. That'll leave us with x times x plus 3 minus x plus 1 times 2x plus 7. And that's all equal to 2x plus 7 times x plus 3. Next, we'll expand and combine like terms with what we have. So if I distribute the x, I'll end up with x squared plus 3x on the left side there, minus, now I'm going to FOIL these two binomials together. I'm going to do so in a set of brackets just to stay organized with them, not to forget this negative sign that's out in front. So if I FOIL these together, x plus 1 times 2x plus 7, we'll end up with 2x squared plus 9x plus 7. And then on the right side, FOILing these together will give us 2x squared plus 13x plus 21. Now we'll continue on by rewriting and combining as many terms as we can. On the left side we have x squared plus 3x. If I distribute this negative sign in now to the brackets, we'll have negative 2x squared minus 9x minus 7 equals, and on the right side, 2x squared plus 13x plus 21. Now we'll combine like terms on the left side. We can put these x squared terms together to get negative x squared, and then these x terms together, the 3x and negative 9x, will give us negative 6x, and then we have the minus 7. On the right side, there aren't any like terms to combine. We'll just copy them down as 2x squared plus 13x plus 21. And now we'd like all the terms on one side with 0 on the other, anticipating this to be a quadratic equation to solve. And ideally, I'd like the squared term to remain positive with a positive coefficient. That's already true on the right side, so I'm going to bring all the left terms to the right side and end up with a 0 on the left side. And on the right side, when I add x squared to both sides, I'll have 3x squared. When I add 6x to both sides, I'll have plus 19x, and then when I add 7 to both sides, I'll have plus 28. Now with this quadratic, we'll try factoring, so perhaps there are a couple binomials we could put together here, maybe with a 3x and an x, so that first times first is 3x squared, and then last times last is plus 28. That has factors of 7 and 4 or 14 and 2. We'll have to do a little bit of guess and check to figure out which ones might work here. Let's try a plus 4 with the x and a plus 7 with the 3x, so that we have 3x plus 7 times x plus 4. Then we'll set our factors each equal to 0 since their product is 0. That's the zero product property, which will give us two values. X equals negative 7/3 and x equals negative 4. Of course, this being a rational equation, we should definitely check our solutions, our proposed solutions. So we should check negative 7/3, and we should check both negative 4 as well. You can check even with a calculator by plugging our answers in the left side of the equation. Just plug them in carefully in a calculator, especially the fraction. And then if you compute the value, it should give you 1, and if it does, that would verify that these are both solutions, and in fact, they both are, which means there are no extraneous solutions. So we'll mark both answers that we got originally as our two solutions.